Welcome everyone. Today we embark on one of the most fascinating and visually rich journeys in organic chemistry, the world of stereochemistry. Have you ever wondered why two molecules with the exact same molecular formula and connectivity can behave so differently in the human body? Or how a single geometric difference in a double bond can mean the difference between a life-saving drug and a harmful compound? The answer lies in the three-dimensional arrangement of atom in space. In this session, we will unravel the elegant rules that chemists use to describe and assign molecular geometry. Specifically, the R and S system for chiral centers and E and Z system for geometric isomers. By the end of this topic, you will not only be able to assign configurations with confidence, but also appreciate why stereochemistry sits at the very heart of the drug design, biochemistry, and modern synthetic chemistry. So, sharpen your pencil, open your minds, and let us dive into the beautiful three-dimensional world of molecules. Before we move on to the assignment of absolute configuration for RS enantiomers and also E and Z geometrical isomerism, we also need to discuss some of the importance behind these absolute configuration assignments. First one is the biological activity and pharmacology. So R and S configurations of chiral molecules are critically important in drug design as enantiomers can exhibit vastly different biological activities. For example, one enantiomer may be therapeutic while the other is toxic or inactive as seen in thalidomide during our class sessions. And drug safety and stereoselectivity, determining absolute configuration ensures the correct enantiomer is synthesized and administered in pharmaceutical compounds, preventing harmful side effects caused by mirror image molecules interacting differently with chiral biological receptors and enzymes. The third one is the geometrical isomerism in biological system. Easy isomerism is essential in biochemistry. For example, in recent science, the conversion of 11-cis retinol to 11-trans retinol upon light absorption is fundamental molecular event that triggers the visual signal in the human eye, demonstrating how geometrical configuration directly controls biological function. When it comes to industrial and agricultural application, in agrochemicals and material science, E and Z configurations determine the physical property, stability, and efficacy of compounds such as pesticides, polymers, and dyes, where cis and trans isomers can behave as entirely different substances. Finally, the synthetic chemistry and quality control. The accurate determination of both R and S and E and Z configuration is indispensable in asymmetric synthesis and quality control of fine chemicals, ensuring that the correct stereoisomer is produced with a high purity, which is a regulatory requirement in the pharmaceutical and clinical industries. Now let's move on to assign the absolute configuration for RS enantiomas based on the Kohn-Ingold-Prelog or CIP priority rules. However, one has to keep in mind that carbon with the four different substituents are considered as a stereogenic molecule or a chiral molecule. Whatever the example given here, the carbon with the four different groups, and certainly it's a chiral or stereo molecule, and we need to assign the priority for each substituent present in the carbon center. So first one is the rule one. First one is the based on the atomic number. Bromine as being at highest atomic number with 35, it gets first priority, followed by chlorine with the 17 atomic number, and then fluorine with 9 atomic number. And finally, hydrogen is having the least atomic number 1. Hence, whatever you get the priority, just move the arc. It moves in the uh, clockwise direction, then it is called R. R, the letter is coming from the Latin word, it's called rectus, and also the meaning is right. And this being the clockwise direction, and also it perfectly fits into the CIP rule because we keep the lowest priority group away from our view, hence it can be considered as such, that is the R absolute configuration. When it comes to the same molecule but position of bromine and fluorine, they considerably differ. And now when you assign the priority for this, Same assignment based on the atomic number. However, the bromine is in the other side, hence the arc moving in the anti-clockwise direction. Therefore, it is called S. S is nothing but sinister in Latin, and it's called counterclockwise. In cases of ties, use the next atom along the chain and use rule number 1. So in order to avoid the confusion, here you can see that the CH2OH and the CH2CH3. The first atom, the carbon having two hydrogen, subsequently it has oxygen in the first one. Here it's oxygen. In this case, it's a carbon. So since oxygen is going to be a higher atomic number A with 8 and carbon is only having 6, then this particular substituent gets first priority, and the other CH2CH3 gets a second priority over methyl group. Methyl group is going to be third priority, and as usual, the hydrogen being 1 in terms of atomic number. Therefore, when you give the rotation, it becomes S. Since the least or lowest priority group is kept away from our view, whatever the assignment comes, we are supposed to take as such. Therefore, the absolute configuration of this molecule is S. Let's consider two more steps where all ligands in a given sphere must be explored before proceeding to the next. That's a principle of outward exploration. The given molecule, if you carefully look into that, the hydrogen is placed in the vertical line. Therefore, whatever it comes, we are supposed to take as such. And hydroxy gets the first priority, oxygen with 8 atomic number. And then carboxylic acid is the second, and the methyl is the third, and hydrogen is the fourth one. And in this case, hydrogen is kept on the vertical line. It's obvious that it's away from our view. Whatever the assignment you get, like a rotation, it's in the anti-clockwise direction, then the absolute configuration of this particular molecule is going to be S. And next one is each atom at a multiple bond is associated with a phantom, that is called duplicate or triplicate of the species at the other end of the multiple bond. Hence, we have to carefully give the assignment. C, carbon attached with the OH, carbon attached with oxygen. So carbon attached with the oxygen directly, it's a double bond, and the carbon attached with the OH is a single bond. Hence, the double bond would get the first priority. The carbon with the double bond, it would get first priority over carbon with OH group directly attached with the carbon. This gets the second priority because this will be considered as carbon is attached with two oxygen, like this phantom, oxygen and oxygen. So whenever you see the molecule with carbon with a double bond O and carbon directly attached to oxygen OH, then this gets the first priority, and the OH would get second priority. In this case, the carbon is directly attached with oxygen, then it gets first priority. Whereas the here in the carboxylic acid, the carbon is connected to first carbon, then only the oxygen. Therefore, it gets second priority. We should not have any confusion over this. Now, let us assign the RS configuration for each of the following molecules. And let's discuss the first three examples. They are interesting because if you look at the molecule carefully, the first three molecule, a carbon with the four different substituent, all of them are same. Only the position differs. Once you understand these three molecules, it would be very useful for anyone to assign the absolute configuration after seeing the molecule, whether it's a R or S. In the first case scenario, where iodine gets first priority and bromine gets second priority and fluorine gets third priority, right? And hydrogen is kept away from our view. It's a fourth priority default because the atomic number is 1. Hence, when you give the rotation, iodine, bromine, and fluorine, and this is the anti-clockwise direction, whatever absolute configuration comes, we are supposed to take. This is yes, anti-clockwise direction. And because why it is because of the hydrogen is kept away from our view, therefore no need to change anything. When it comes to second example, same groups but position of the groups differ. In this case, Iodine is here, first priority, bromine is second, fluorine is third, and hydrogen is fourth. But only a slight change is there. The first case, the hydrogen is located away from our view, whereas in the second case, the hydrogen is kept close to our view. Hence, whatever outcome comes, it should be taken opposite. So 1, 2, 3, it's going to be R. However, we just need to reverse it. So therefore, the absolute configuration is going to be S. The first two cases only just playing with the lowest priority group kept away from our view or close to our view. The next third example is very interesting because hydrogen is neither close to our view nor away from our view, but it is kept on the plane. What we are supposed to do in this case? These three examples, if you carefully look into that and if you know how to assign, then it will not be a problem. So now if you look at this particular molecule, the iodine gets first priority, bromine gets second priority, fluorine gets third, hydrogen is fourth. But the only thing is hydrogen is kept on the plane. What can we do now? We just need to swap. The hydrogen should be taken to the fluorine position because the hydrogen will come away from our view. Then fluorine should be brought to the hydrogen place. Then now you can say uh, hydrogen and then fluorine. The other two substituents would remain in the same place, iodine and then bromide. Okay. So now if you give the atomic number 1, 2, 3, the least priority group stays away from our view. Hence, it's coming as yes. It's a anti-clockwise direction. Since we have done only one swap of two groups, whatever outcomes, it should be reversed. Then the outcome would be R. Otherwise, you can go for one more swap, like without disturbing the least priority group, you do any two groups exchange, then whatever outcomes as such we are supposed to take. Otherwise, just remember, only you have to take the least priority group. It should be kept away from our view. Hence, then the absolute configuration, whatever is the outcome, it should be opposite. The fourth example is interesting. It falls within these three groups, right? So hydrogen, the hydroxy is the first one, and this will get second priority. CH2NH2 is the third priority. The hydrogen is the fourth one. But again, if you look into that, this particular example falls in this category, the third category, right? So hydrogen is on the plane, hence we just need to take it away from our view. Hence the hydrogen should be taken to CH2NH2. What would be the outcome? Now if you see that hydrogen and you bring the CH2NH2 and then OH and CN. So if you carefully look into that, this carbon is attached with the nitrogen, right? And this carbon, it has attached with the nitrogen. However, this carbon has triple bond. The bonding between carbon and nitrogen is triple bond. Therefore, it is equivalent to 3 nitrogen attachment, right? That's a phantom carbon, right? So therefore, this gets higher priority. Hence, the hydroxy is going to be 1, the nitrile is the 2, and then this one is the 3. The fourth one is the least priority group. Then if you give the rotation, it's coming as yes. Then since we have done one swap of two groups, therefore the outcome would be R. This particular molecule, whatever you get, it's going to be R. Okay. So one has to remember this small trick. If the hydrogen is away from our view or close to our view, or if it is placed on the plane, how to change and how to assign the absolute configuration. It becomes very easy for us to assign the absolute configuration of any given molecule. And again, if you look into this particular molecule, what happens? This also falling in the one of the categories where hydrogen is close to our view. Hence, if you assign the absolute configuration, first one is the carbon, this with two oxygens, first priority. The second one is a carbon with the hydroxy group. Third one is a carbon with triple bond carbon. The fourth one is this one. So if you give the rotation, it's going to be R. However, hydrogen is kept close to our view, hence it should be reversed. R will become S, right? Yeah. This one is another example. The hydroxy gets first priority. This triple bond gets second priority. Double bond gets third priority. And CH3 is the fourth priority. However, the CH3 is the lowest priority group. Is as usual kept away from our view. So no need to worry about it. Whatever the assignment comes, we are supposed to take as such. So it is going to be R. It's in the clockwise direction. And in this case, the seventh one, the bromine gets first priority. Second is the chlorine. Third is the methyl. And fourth is the hydrogen. But if you carefully look into that, hydrogen is kept on the plane. It falls in the third category of the molecule. Hence, we just need to swap two groups where you bring the hydrogen to the bromine place because we need to keep away from our view, and bromine takes the hydrogen place, and chlorine and CH3 remains, they remain in the same place, right? Chlorine and CH3. So if you give the assignment, bromine gets first, chlorine and CH3. Then if you give the rotation, it's anti-clockwise. So the configuration what we get is yes. However, since we have done one swap of two groups, then the original configuration will be R. You have to just understand this particular trick. And eighth one, if you carefully look into that, it's having two identical groups. Therefore, it is not chiral. Hence, we are not going to give any assignment for this. Yeah. So far, what we have seen is carbon with four different groups, either close to our view or away from our view. It's a direct example. But if the molecules are projected in a Fisher projection, how to assign the absolute configuration? Let us discuss the first one. If you see this, the nitrogen and hydrogen, they are close to our view. They are present in the horizontal line, whereas carboxylic acid and methyl groups, they are away from our view. It's representing the dotted line, that's a vertical line. Okay, so when you give the priority, nitrogen gets the first priority and carboxylic acid is the second priority and methyl is the third priority. It's very simple. Since hydrogen is close to our view, whatever the outcome comes, the rotation is R, then we are supposed to take it as S, or should be taken as S. This is very simple because this Fisher projection has only one chiral center. When the Fisher projection has two chiral center, the molecule has two chiral center, then that becomes slightly complex. We have to assign each carbon what is the absolute configuration. The first, let us see the first one. Here you can say that nitrogen is the first priority. Second one is the this one where carbon with the chlorine and then methyl. So hence, fourth one is the hydrogen. Again, hydrogen is kept close to our view. So whatever outcome, that is the right clockwise direction, it's going to be R. However, since hydrogen is kept close to our view, then it becomes the original configuration would be yes. And the next one, this particular carbon being a chiral carbon, hence we need to give the assignment. If you look into that, fluorine gets first priority, followed by carboxylic acid, because carboxylic acid, it has two oxygen, double bond with a single bond, and oxygen gets higher priority because atomic number is 8 over nitrogen being a 7. So this one is a second and third, and fourth one would be methyl. Again, the lowest priority, in this case, the lowest priority group is kept close to our view. Therefore, just give the assignment. The direction is 1, 2, 3. Hence, it's coming as a yes. So yes should be reversed into R because of the least priority group is kept close to our view. In order to correct it, then we change the configuration, whatever we get, then it's going to be R. So in this case, you just need to remember how to assign the absolute configuration for a given molecule, whether it's a chiral center with the normal one or in the Fisher projection based. Yeah.